In this discussion video, we will talk about how to conceptualize 0 over 0 indeterminate forms. So recall that an indeterminate form is a limit that we cannot determine simply. So we cannot determine simply by plugging in and some thought. So I want to first talk about some determinate limit examples. So ones that we can determine it simply by plugging in and maybe a little bit of thought. And then I'm going to give some examples and then talk about their graphs so we can visualize them. Okay, so the first example is the limit as x approaches 2 of x plus 3. So first step is let's plug in 2 and we'll get 5. So let's draw the graph of this. I'll draw some axes and let's draw the graph of y equals x plus 3. So this x plus 3 function. So that's a line. The y-intercept is 3 and the slope is 1. So we are going to draw a line that has y-intercept at 3, the slope is 1. And visually, so as x approaches 2, I'm going to mark 2 on the x-axis. And at that point, the y value is 5. So visually, when x is approaching a number like 2, that happens to be in the domain of this function, and this function in this example was just a line, the y values are just going to get super close to whatever the y value is at that point on the graph. All right, let's look at another example, slightly different. Let's do the limit as x approaches 2 of 1 over x minus 2. If we plug into this, we get 1 over 0. And we've seen before that with a 1 over 0 type situation, we would end up doing one-sided limits. And we've also seen before that a graph like this, when we do have a non-0 over 0 situation happening, the graph is going to have a vertical asymptote at x equals 2. So I'm going to draw a picture. I'm going to draw some axes, and the graph of this at 2, this is going to have a vertical asymptote. And the graph is really similar to the graph of 1 over x, a hyperbola. It's just shifted 2 units to the right. So there's going to be one piece over here and one piece over here. But in general, the way we could determine what's happening on either side of this number as x approaches 2 from the left and from the right is to use one-sided limits. We'll use one-sided limits to see if this overall limit, to see if it could either be infinity, if from both sides it went up to infinity, it could be negative infinity, if it went down to negative infinity from both sides, or it could be d and e, like it ends up being in this problem because from either side it's different. One from the left it's negative infinity, from the right is positive infinity. But in both of these examples of these determinate limits, I know what's going on with the graph. Maybe with just a little bit of thought, thinking about the one-sided limits for the second example, but there isn't ambiguity about what the graph should look like. And now let's look at indeterminates for contrast. So with an indeterminate, let's give some examples. Let's first do the limit as x approaches 0 of 4x over x. And if I started off by plugging in, I'll get 0 on the top and 0 on the bottom. So that's an indeterminate. And our strategy for those is we simplify. And if we were to simplify this, we get the limit as x approaches 0. We would cancel the x's and just get 4. And now there's no x's left in this. So if I try to plug 0 in, there's nothing to plug into, so I just get 4. And if I draw the graph, let's have a column here for the graphs of these. So let me draw some axes. Our function here, 4x over x, this just simplifies to 4 as long as x is not 0. Because if x is 0, it makes the denominator 0, and that makes the fraction undefined. So the graph should look like the graph of y equals 4. Let's put 4 on the y-axis. Should look like the graph of y equals 4, which is horizontal line, but there should be a hole there because I can't actually plug in x equals 0. So as x gets really, really close to 0 from the left-hand side or from the right-hand side, the y values get really, really close to the y value of the hole, which is 4. And that's why the limit is 4. Okay, so an indeterminate limit can sometimes be a finite number, like 4. Let's look at another example. Limit as x approaches 0 of x over x squared. Let's start it off by plugging in. I'll get 0 over 0 if I do, so I simplify. And I'll get the limit as x approaches 0. Let's cancel an x on the top and the bottom to get 1 over x. And this is a graph that we know. This is just a basic hyperbola graph. 1 over x has one piece over here. Has a vertical asymptote at the y-axis. One piece over here. And by looking at this graph, we can see that this limit does not exist. Because as you approach 0 from the left, the y values are going to negative infinity. And as you approach 0 from the right, the y values are going to positive infinity. So this does not exist. So an indeterminate limit can be does not exist with a vertical asymptote like this. Let's do one more example. What if I have the limit as x approaches 0 of x over x to the third? If I plug in here, I get 0 over 0 again. So we simplify to get the limit as x approaches 0 of 1 over x squared. Okay, so this might be something that we know the graph of. I'm just going to go ahead and graph it. And let me label this previous one. This is y equals 1 over x. Now I'll have y equals 1 over x squared. If I graph this, it's similar to the graph of 1 over x, except there's one piece here. There's one piece here. It's a little bit kind of skinnier than the graph of 1 over x is. That's a little bit harder to show while I'm graphing it by hand here. But both of the pieces go up to infinity as x gets close to 0. So I could see that this limit is going to be infinity from this graph. If I didn't have this graph, I could still do this pretty quickly. We can now use, if I were to plug into here, I would get 1 over 0. A non-zero over 0, which means use one-sided limits. We would use one-sided limits to show this, to show that it's infinity from both of the sides. So as we're seeing in these examples of an indeterminate form limits, they can be finite numbers like 4, like the first one was. They could be d and e, like the second one was. They could be infinity, or even negative infinity, if I just had a negative sign here. They could be anything, in fact. So let's write that down. That is a key observation. Indeterminate forms can be anything. We have to simplify it a bit to know what it is, but we can make them be anything that we want. Graphically, when we get a 0 over 0 situation, we're not sure if the graph has a hole like that first indeterminate example did, or a vertical asymptote like the second two indeterminate examples did. And because we're unsure of that, if I just see 0 over 0 and I have no other information, I'm unsure whether there's a hole or there's going to be a vertical asymptote. So we must simplify to gain more information. And that's conceptually why we simplify with indeterminate form limits.